Good evening from the woods of Maine. It is Christmas Eve. It is again frigid out. So much so, I am having the wood stove and the Renai heater battle it out. See who can do the job. Anyway, so last time we spoke, it was regarding the Permian Triassic extinction event, which wiped out about 90 to 95% of life. And now we have moved into the Triassic period, and oh my, have things changed. We went from a beautiful, warm, lush, tropical world through the Carboniferous to Gondwanaland, going down over the poles, having an ice age, and then the climate began to cool. And the warm, lush world that the amphibians were just thriving in began to change. And as it did, things began to dry out as Pangaea came together. And once Pangaea did come together, it actually abruptly halted the world equatorial ocean current that basically keeps the oceans very mixed. So, not to mention the massive mountain range that occurred when Pangaea came together in the form of the Appalachian Mountains on the equator. We had a lot of things going on where sediment and tons of carbon or carbonic acid was being thrown into the Paleotethys Ocean for the most part. But then it becomes really the Tethys Ocean. There's a dividing line in there. And all of a sudden, everything started to just go haywire. The oceans became acidic. Therefore, things that, can more or less move carbon dioxide around in the ocean were not precipitating. And so the oceans become acidic. The stagnant the Paleotethys and the Tethys Ocean probably became somewhat stagnant. The fact that there really was no way for the oceans to go through, and at the western end of that, the Tethys Ocean would have been probably chocolatish water from the rivers pouring out, sort of like off of the Amazon Basin. And so now the oceans are becoming anoxic. Things are not going good for the world at this point in time. That was really where I was going with that. And then we get a massive spike in temperatures right towards the end of the Permian period. And the Siberian traps erupt. And once the Siberian traps erupt, it's just everything you didn't need. It goes right up through an area of massive coal fields, so it's just like erupting through gasoline. And we just have already a very stressed world, massive temperature fluctuations, deserts forming, amphibians are no longer being the king of the town. It's moving, the reptiles are now starting to come into form because reptiles can get away from the water. And now the temperatures are spiking and things are drying out, and then the mother of all eruptions comes and just absolutely again comes up through what is essentially a reservoir of gasoline, and it just decimates everything. And most likely one could make a case that the hardest hit of these was without a doubt the amphibians, but they had it coming. They were already starting to get whacked in the middle of this the Permian, and it was just really the icing on the cake, and yet they still survive. So, frogs and stuff are around today, so it's just the amphibians begin to diversify, and the large ones get taken out, and the small ones are what we see around today. So anyways, our once lush, tropical, beautiful area becomes a desert-like area, very dry on the western slopes of it, at least equatorially. The temperate regions north and south in Pangaea are likely very desert-like. And then you're going to get down to cold poles and still dry, but the equatorial region, especially the central eastern area of Pangaea, is just a choke full of jungle of just massive amounts of erosion and mud and all sorts of stuff just just getting dumped into the ocean there. So an interesting setup, and a setup that really life does not really do well when it occurs. So the Triassic period is notable, of course, because it's a transition period from the Paleozoic to the Mesozoic, and anybody can tell you that. What's the Mesozoic associated with? It's associated with the dinosaurs, and it makes total sense that the dinosaurs came out of this because everything dried out, and the species ruling the show up until this time, at least through the Carboniferous when everything was warm and lush, were the amphibians. They thrived in that. They could get away. They didn't need to go far because there was just water and everything was wet. But now everything is dried out. You need a tougher skin because if amphibians go away from the water, they die. So it wasn't working anymore. And so the next step in the evolution was to create something that could move away from the water, i.e. coming in the form of a reptile. It's just the next step in evolution. All right, here we go. So the Triassic, 245 million years ago, we are seeing notable rifting here, some creeping up in here. The Caledonians have not split off yet, but we're starting to see something here. So this over here will trail off to the in this orientation it's the east. In fact, I think it is just the east. The new split, there's Finland here and Baltica here. This is probably something related to the Mediterranean or offshoot of the Tethys Ocean there. And then of course we've got Northern Africa here, South America here, the suture between South America and Africa. And North America, Laurentia is still Amazonia, Africa, is going to start separating. It's serendipitous that wherever you come together, that's where you separate it. It's a weak spot, so it worked once, worked twice, worked 3 times, and you can see the lines right here. These are extension. This is an extensional environment. So this is going this way. This is going this way. Everything's getting pulled out. There's lots of normal faulting in here. So everything is just kind of going like that because everything's pulling and the rocks drop down. And eventually the sea is going to come through, and eventually this will thin out. Voluminous amounts of lava are going to come through, and this Africa goes her way, North America goes her way, and South America goes this way, and then parts of this become the isthmus of Central America. 230 million years ago, here we are. This is getting noticeably a lot longer. It's getting some blue in there. You're getting some possible oceanic crust starting to come. This is extended considerably now. The oceans are starting to try and invade in here. And pretty soon this is just a great indicator that this is about to separate. 210 million years ago, again, this is continuing to extend. It's going to start moving its way into here. This is moving this way. This is getting thinner. At this point, you're probably starting to get flood basalt eruptions. I would not be surprised if there are a few starting to come there. And of course, Baltica, what is now Europe, is now beginning to rift off of Greenland and Labrador. So, timeline chart opening of the Atlantic. The opening of the Atlantic is right here. It's the furthest point we go. After this, we would start, we haven't started to close it yet, so we don't really go any further with it. But we are here at a little less than 200 million. The North Atlantic begins to open. And as it does, it will continue right up until today. So we have now completed our Wilson cycle. We had a closed ocean where the Atlantic is now in the form of the Iapetus. The Grenville orogeny closed its own ocean. That is a different ocean. And then the Iapetus Ocean opened, and then it began to close in sequences here with the Taconic, the Silicic, the Acadian, the accretion of the Swanee and the Maguma provinces, and then, of course, Africa hits. But then Pangaea forms, and just like Rodinia formed from the Grenville orogeny, and the ocean is reopened again. So one full cycle. Grenville cycle to Alleghenian is one full cycle. Now we are starting the rifting process, and we are now opening another ocean. And theoretically, it's going to happen all over again. So where the pieces of land, I mean, you can kind of think that maybe it already is because we know we got action going off of right off of the Strait of Gibraltar. There's something going on there, as well as we have the Puerto Rican trench down there in the down near Puerto Rico, and the islands there. That arc is active and moving across the ocean. There is also one down in very south that's connected more or less between Antarctica and South America, and that one is active and moving across. So theoretically, there could be other ones forming, but those are on their move, and they're eventually going to go across that ocean and slam something into the west coast of Africa, and the Puerto Rican trench will theoretically keep going, depending, I guess, I think it's going faster than it should eventually. If the crust is moving at one speed and it needs to be going faster than it's moving away, it'll eventually reach the mid-ocean ridge and could even go right across it. And then if it does, it's going to end up crashing into, well, whatever's in front of that. I don't know, Azores maybe? But anyway, different conversation. So we are now opening the Atlantic. So Triassic period tectonics. We are down here. We are spreading out. This was the highlight of the Appalachian orogeny. The Grenville's here. We rifted it. We had a passive margin. We had an offshore island arc in the form of tectonic island arc. It slammed in. Then Gandaria came in, and then Avalonia came in, and then Africa came across and crashed. And then we've got the highlight of the Alleghenian orogeny here. And then, of course, everything wears down, gets light, and now things are pulling apart again. And eventually they're going to be just like this. This is today. We got our plateau, our valley and ridge province, which is what's left of these and so forth. And you have the nice passive margin of the Atlantic Ocean. So we have all sorts of what we call classic wedges here from the Appalachians, just, dropping everything they had. But these probably go out somewhere out here by, I mean, it's been, 50 million years of weathering. It's going to produce a massive amount of erosion. Probably in the form of this. It's a little bit lifted here, and of course, it's going to have very thick wedges on either side of it that will thin out because what happens is the basin, the mountain range will erode and it will just put all sorts of debris out here. The debris weighs a lot. It starts to bend down, and then it just keeps piling. But the further away you go, it gets thinner. But right now, we're extending and getting pulled out, and that's marked by all these volcanoes here. These are not like the volcanoes we had when the Iapetus was closing. These are very different. They're producing very mafic, very fluid-like lava. That's because underneath here the weight of the mountains has decreased so much. And the roots of the mountains are pushed down so far that as they lift back out, it's called, I've referred to this a million times, it's decompressional melting, and it helps force this way and then Africa this way, and you have these massive basaltic eruptions. You can see them in Connecticut, near Hartford, the Connecticut Rift Valley, Newark, New Jersey, the Palisades Sill. These are all indicators of the opening of the Atlantic Ocean. So if you're ever there and you just go look at the Palisades Hill, it's gigantic, and it's just a big flood basalt that was helping force things out. New England 230 million years ago might have looked something like this. I think this is modern Nevada. Nevada is an area that has extensional tectonics right now, so the crust is getting thinner. California side is moving away quicker, is moving away from the Colorado side. I mean, as a general reference, if you were to stand in the middle, that's what's happening. But the whole thing is actually moving west-northwest. But as it happens, these blocks drop, and you get these grabens in here. So this is, in this picture, you would imagine that this is west and this is east, and this is going this way, this is going this way, and so in between these two, you've got a dropped block. If something stretches it, it drops. So this might be a normal fault block down here, a graben, and it fills up with sediment. Oh, and everything was very, very dry too. A lot of things were dry. Maybe not so much here, but you get outside you get in the shadow of the the rain shadow of the mountains, it's going to get very dry in the shadows of that. So might not exactly be New England. New England might be a little bit more wet, but it's still the same ideas going on. All right, Triassic landscape. We have here what looks to be a dinosaur or collection of them, and this is a Triassic. Would be a Triassic landscape, possibly. I believe I pilfered it from a Jurassic website. I don't know why I would use anything else, but let's assume I did. In any case, what you have here is you've now got the reptiles have evolved into something different. And what they've done is there was a design that worked very well in the Permian, and what these guys did is they just kind of honed it a little bit more. And the classic traits of an archaeosaur, which I believe these are archaeosaurs, and I have to specify this, and I'm glad I just watched something about this because I did not know this either. But there is no one specific dinosaur that you could say is the transition point. It's a group of dinosaurs called the archaeosaurs that really indicate we either, at least up until last year when I was just doing some research, we've either never found an exact one or it's just there's a bunch. And it makes more sense. I mean, how could you ever just pinpoint the exact, it doesn't work that way. You see progression. And so in the early Permian, when everything became dry and in the early Triassic, when everything became dry and what have you, the reptiles just there was so much death that there was just everything was left wide open. So all you really needed was a food source to ignite it. And as it turns out, of course, the marine habitats, fared a little bit better. And in marine habitats, that's where your food chain started really to get going. And it started very small and worked its way up. And so it took about 20, 30 million years to really get things, kicking. We'll even say 15 or 20. I mean, this is what, so the extinction event's at 250. So this is 20 million years. So the trees have changed their game a little bit. A couple of new species have shown up here. They've become more resilient. The few reptiles that made the jump started off small and slowly began to grow. And this is all because the ocean started to get their act together, soon after the extinction event by doing microscopic, getting phytoplankton, getting the things that you need. You need the basic food source in order for the rest of everything to work. And once you got the basic fundamentals down, then the fish could start to evolve, and the cephalopods and the ammonites, which the mollusks do very well in the Mesozoic era. In fact, they are the index fossils, a lot of them for certain sedimentary units. So and they're the ones that get their kick, because once you got that ocean, the acidity down, and there's some oxygen in there, those cephalopods just go nuts and they diversify and they become the very dominant species early on. And of course, the things that eat those, the fish and what have you, and the things that eat fish and what have you, and the things that eat fish, it spreads out, and you're providing nutrients. And this is the new design. This is reptile 2.0. It's got big burly back legs but smaller front ones. You've developed a thinner body for the most part. You're bipedal. You have teeth. You have teeth in here that are individually socketed, and that's a very important thing, and that is a unique thing to a dinosaur. So this group here is what really gives rise to the dinosaurs. And again, it didn't stay completely horrible forever. The Triassic landscape did begin to change, and the fires went out and everything moved on. Yeah, well, I don't think that's Jurassic, but anyway, this is a good idea of how things were probably beginning to come back. So let's just go back for a minute and think about vertebrate evolution, because once you get past things like mollusks and sponges and corals and stuff, well, you got really the majority of the larger animals are all chordates, and that means they had a chord. And we begin somewhere down here in the ancient, the Precambrian. I'm not going to go into that, but the lineage is just so obvious. This is your vertebrae. This is not really this has a cord. These two guys here have cords, which means they have a nerve center in, somewhere in there that basically operates things more or less, So these go right back to our ancestral chordate. A true vertebrate starts right around the Cambrian explosion, and it begins to diversify. And it always starts with, you've got like these lamprey-like organisms here that basically they evolve into fish. You got your lobe fin fish and your ray fin fish, which of course these coming up here. But so what needs to happen with these guys is that everything's great. Now you've got so you had a nerve area, and then you had something that became an actual network and became a vertebrate, which is great, but you need to get some teeth. So the next step was to actually change whatever biting mechanism you had. You needed to change that, and that came in the form of plates. Some of the earliest predators, back, you go way back, they were pretty nuts, and they had actual plates, like bony plates for a mouth, and they were just absolutely, vicious, big creatures. Not sharks, but they could easily kill a shark. But so the jaws end up coming out of one of the back gills. The back gills eventually, one of the back gills begins to evolve, and then it ends up forming a jaw-like structure. And that's how the jaws come along. So now you're going up and you get your first fish and stuff here, and then you have a lung or a lung derivative, and that comes in the form of lungfishes, or it's ray finned or lobe finned. Yes, I think that's what it is. And so of course you move forward, and so now these guys are going to end up trying to get on land. Well, when you get on land, you've moved into the amphibian, and now you become a tetrapod. So from below here, you're a chordate. Above here, you're a vertebrate. Once you get past here, you become a tetrapod, which is everything, pretty much. And then something really big happens right here. The amniotic egg. And the amniotic egg separates us from the amphibians. The amphibians have to go back to the water. You always see eggs in the water of amphibians and frogs and what have you. And that's because they do not produce internally. That comes in the form of the reptile, the bird, and the mammal. And the amniotic egg is what solves a lot of our problems. Now these guys can move around, they can get away, they can go, they don't need to stay dry. And of course, this falls up into your reptiles. And then you have two basic paths of reptiles. You have the croc hip and the bird hip. You get the dinosaurs on both sides. These end up going to birds. And then, of course, once hair is developed to keep you warm and regulate, that's the mammals. So, in a nutshell, so not all chordates are amniotes, but every amniote. Oh, that doesn't work either. Yeah. Every amniote is a chordote. Every amniote is a tetrapod. Every amniote is a vertebrate. Every tetrapod is a vertebrate. Every tetrapod is a chordate. Every vertebrate is a chordate. But you can't go in reverse. This is the steps of evolution. Okay, so the difference between a dinosaur and a reptile is the hip, and that's what makes them kind of special. The hip is something that really is sort of a big improvement. Most reptiles, you've seen them, they kind of sprawl. You see an alligator, it walks with its legs out to the side, and that's great, and that worked for a very long time. But over time, there are improvements that are made on this. I mean, this is good for the design of that creature for sure. But for us, it really wouldn't work. You just can't go very fast. That's the thing. You have quick burst of energy, but you're not going very far. We're going to not talk about these because I don't know much about them. But we, mammals and dinosaurs, walk like this. And we have a socket that goes in here. And our weight is supported by our legs. It's not being supported just by this bone right here. It's being supported by everything, including the hip. So this is a much better. This allows you to move quickly. It allows you to have rotation. This socket is not a socket. It's really just a fin. I mean, it just sort of goes back and forth. You know, it can't really do much. It's a thing that slots in like this. We have a, you know, it's called a ball socket. We have a ball socket. It's much more advantageous over this design to have a ball circuit. Dinosaurs, as it turns out, actually have the same hip. So that's one of the key important differences between a reptile and a dinosaur. Now, the dinosaur also has individually socketed teeth, and that was a huge improvement. The dinosaur has a different, has palliated bones in its mouth, meaning that the roof of the mouth has very strong and robust bones. That is much different than reptiles. What else does it have? The bones are different. You know, reptiles are sort of squatty bones. That the dinosaur has a much more pronounced bone. The bone ratios are much different than they are in a reptile, and not to mention the fact that they're bipedal. I don't know really any reptiles that are bipedal, but a dinosaur is fully bipedal. Although they could walk on fours if they need to, but for the most part they're bipedal. So those are just a few things that make the dinosaurs different than a reptile. All right. This is one of the first known common ancestors to the dinosaur 243 million years ago. Again, notice the difference between the reptiles that we had been seeing to what we see now. Leg is clearly under the actual animal. We have shortened forelimbs with robust back limbs, a balancing tail, and a long neck. A completely different design, much sleeker, much quicker, much less energy needed to keep it going. And this is the design that dinosaurs, for the most part in the beginning, take after. And it stays pretty true, although we see, you know, dinosaurs diverge just gigantically in the Jurassic period. But this is the shape that gets them going. And almost all, even a sauropod, even a brachiosaur, they all come from this guy right here. So they all share the same shit. All right. So, dinosaur family tree. I said that we have a bird hip, and then we have a lizard hip. And that's again because you know, these are more shaped like birds, and these are more shaped like you know, croc hip or whatever. So, and it's very obvious because everything that's on this side is a four-legged animal for the most part. Yet everything on this side is almost bipedal. So the sauropod has now been moved into its own category. This has just happened recently. Hard to really, it was always grouped over here. You know, it has this hip, but yet it shares a lot of other characteristics with this. So, you know, in a sense, I don't know why. It might just be an intermediate animal. I don't know. But in any case, it's more bird-hipped. And of course, if you go up the, you know, another thing about theropods, bird-hipped dinosaurs, is that almost all of them are meat eaters. You know, the duckbills, oh no, they're over here. They almost, it's almost an exclusive you know, part of being a member of that club is you have to be sort of a meat eater, and most of them are. I mean, I think there are a couple that aren't, but you know, you can see the lineage right here. This is an arms race. So basically, in the Jurassic, the herbivores are winning as far as size goes. They outgrow everything very quickly, and when you're that big, you're just, you know, you're not really nothing's going to bother you unless you're only when you're young. But our biggest predators, more or less, are lagging behind. But they start catching on. You know, the allosaurs are fairly gnarly. You know, they're going to be something that's a force to be reckoned with. And then, of course, you know, you go further into that, and you get your tyrannosaurs and your your Giganosaurus, and all these crazy, you know, things that are of nightmares. But they all end up, they don't make it past obviously the extinction event, and they end up being evolving into birds. That's where the lineage goes. And if you really look at a bird, uh, you know, you can kind of see it. They have the legs. It looks just like a dinosaur would look like. You know, the feet. You know, the way they walk. It doesn't take a lot of it. They're just a smaller version. And you think about it, when you have the KT extinction, again, it's kind of the similar problems as the Permian extinction. Nothing big makes it through. You need to, if you're going to make it through an extinction, you need to be small and require very little energy to keep yourself going. And the big meat eaters did well. They of course didn't have it because there wasn't any vegetation for the large plant eaters to eat, so they were gone. And when you take away that food source, the other one goes with it. So anyway, so over here, you know, we've got some more of our famous dinosaurs. Everybody knows. We know about the stegosaurs. Everybody always, you know, whenever I see the stegosaur and the tyrannosaur in the same screen, it pisses me off because the stegosaurs are so much older, and they're really a Jurassic marking dinosaur, and they just never saw each other. They were separated by 100 million years. You know, you got your Triceratops. These guys over here, they evolved into just, again, once these meat-eating dinosaurs caught up and started becoming an issue, the plant eaters once again needed to come up with a defensive mechanism, and it came in the form of, well, clubs, armor, deadly. Can't think of the name of the I can't think of the name of the shield on the back of the Triceratops. Not to mention I don't know how long those horns are, but they look like they could be a couple, you know, 6-8 feet maybe. I don't know. They look deadly. So, yeah, plant-eating dinosaurs and meat-eating dinosaurs. There's always an arms race, just like it is today. You know, right now the elephant, you know, not much is going to mess with an elephant. And the same thing with a blue whale. If you're that big, unless you're sick, you know, nothing's going to screw with you. All right. This is an interesting chart, and it's complex, but I'm going to make it simple as I can. Again, 250 was the extinction event. You've got your Archaeosaur. These are the Euroraptor's considered one of the earliest dinosaurs. And what happens is these things split, and one goes down the Ornithischian dinosaurs, which is basically the horned dinosaurs of the, you know, they end up being the horned dinosaurs of the Cretaceous. And what you have is you reduce the, it looks like the fourth and fifth fingers. These guys, doesn't say anything about that. So this guy here has what, loss of the fifth, second and third about the same length. So you're seeing the feet begin to change and the appendages. So what's interesting is as these evolve, you're witnessing, you know, 4-digit hands in the beginning, and then you have hollow bones and a wishbone, so making things lighter, more efficient. Now you move to a pubic boot and a 3-digit hand. That means you don't even have the 4, you just have 3. Hollow cylindrical feathers. Okay, so now feathers are developed here, and again, reduction of the third. Oh, sorry, that one stays. Then you end up, your hands begin to develop, and they end up getting, like, you know, hooks and digging tools, what have you. And then feathers begin to evolve even more. You have elongation of the second finger, and then you end up actually developing a beak. So over time, these animals, what they did is that just due to diet and environment, you ended up kind of, your teeth reduce, and then you end up with a beak. So that's kind of interesting. But so this is sort of the progression. These guys stayed the same. They go on a different path, but this is the path of the theropods going into birds. All right, the opening of the Atlantic near the end of the Triassic. So this was the Iapetus Ocean rift zone. Well, this is where it actually rifted off. It tried a whole bunch of different places, just like it did here. And so I just colored it back in, and then this is the rift of the Atlantic Ocean. And it doesn't take a genius to realize, yeah, there's a few different things to it, but for the most part, it's pretty similar. The difference is here and here. Um, we still have the prominent out here, but yeah, this is this is I always found this fascinating. How one orogeny, um, when it breaks up, will almost absolutely set up the breakup of the next orogeny it comes. It will just be a little further out. So in theory, when the next one comes, the next rift zone will be somewhere out here, and that's all these are. These are transform faults. This is the mid-ocean ridge opening up right here, and eventually, this tried to open up here. It tried to open here. This is the Connecticut Rift Valley right here. There's a Newark one down in here. You've got huge. Oh, these are those are Grenville ones. Sorry, those are twice as old. Well, actually, 3 times as old. But anything in orange is essentially where the continent of Africa tried to break off. And so these are just failed pulses, and then it all came together out here and broke. And again, this embayment right here still shows up right here. And this actually is a piece of the hell is this? This is a piece of it's a piece between Africa and the top of South America. This is a foreign piece, I believe. It's kind of interesting, the whole story about that, as well as this piece, I believe, in here too. Anyway, the opening of the Atlantic near the end of the Triassic period. And again, so if you go back to here, this right here is represented by this right here. And so you just bring these two back, and at one point, this was right here. So that's all these are. I just drew it out. So from stable continent to rifting apart in the Wilson cycle. What has happened now is that the reduction in weight from the massive mountain range that was once here has allowed this root down here to begin to melt. As it melts, it begins to produce a magma source, and it begins injecting, or it's going to start to begin injecting up through here. As you can see, it has here. It's going to start to keep going, and eventually this is going to start firing up. And as it does, it's going to start spreading and basically pushing everything sideways and trying to get its way out through here. And eventually it succeeds, and you can see how everything begins to crack. And this is where we are right now in the Triassic. And then this is where we are today. So we're on our way to where we're going to be in presently the big giant Atlantic Ocean, but right now we're right here. And this was caused by the erosion of these mountains that allowed this crustal root to melt because it was pushed down to a very hot area of the mantle. As it melted, it started to create a magma source, and then the magma source forced its way up through and separated the continent. So the magma generally begins to rise and melt more crust, making more magma, thus forcing the crust upward and to split apart, i.e. this is rifting. So, yeah, this is how it goes. And the Jurassic period, we have basically we still have Pangaea at the very beginning, but it's totally starting to split up. This ocean, the Tethys Sea, is starting to get subducted. You're getting India's is going to rip off of here in the next 100 million years, but this ocean is now starting to get subducted. 195 million years ago, we can clearly see what is going to become the ocean basin. This is the Gulf of Mexico. Water is now flooding through the rifts, the rifts right here. This is completely now pulled apart. Everything is worn down, and now we have big giant northeast, southwest trending rift valleys that are filling with water, and the crust is becoming thinner and thinner and thinner, and eventually the flood basalts are going to start to fill this area, and eventually these two pieces are going to separate, and we'll have a new ocean. There's also something going on out here. This is going to end up getting, I believe, dragged and then adhered onto the west coast. That will make I think that will be the ancestral Rockies, if I'm not mistaken. 180 million years ago, yep, now we have now the ocean crust is now being formed here. Ocean crust is starting to be formed here. The rifts are elongating. This arc system here is now approaching. There's a subduction zone here, so something's going to happen out here. I want to say laramide, but I might be wrong. And you can see the vast amounts of sediments that have been shed from these mountains. But yep, We're about to become an ocean. And bang, 170 million years ago, we have now separated. And here we are now oceanfront property. The baby Atlantic is just starting. This right here, I believe, might become Cuba or something, or it might become the Yucatan, who knows. But the Gulf of Mexico is going to be right here. Florida is right here. Again, it was a piece right between these two. And then the North Atlantic is right here. The South Atlantic takes considerable more time before it begins to open. And then this arc system is again getting dragged into North America. And you can see an interior seaway right here. This is why the sauropods the dinosaurs start thriving, is you have this huge interior seaway that floods and the continents get flooded and it's really warm. So there's a lot of food. There's a lot of plant growth now. And the dinosaurs just absolutely thrive and kill it. Jurassic, 150 million years ago. Clearly an ocean basin now. You've got... I want to say that's going to be Newfoundland. The South Atlantic still hasn't really done it. I think it's 120 when it breaks. You got your Florida, Bahama thing here. Yeah, could be a piece of Central America or Cuba. I don't know. But now we're getting a new orogeny here on the West Coast, first time in a while. So seaway has restricted a little bit, probably from the lifting of this area right here. But we have rifting starting to make its way up through here. It's starting to edge its way through here. And we have plenty of continental flooding over in this area in Europe and what have you. Jurassic period tectonics, paleogeography 170 million years ago. Big old, what's left of the Appalachian Mountains. Lot of sediment around here. You got an open system right here. Looks like you have a little bit of an interior seaway. You have some new volcanism out here associated with the new trench that's formed off here and subduction taking place. We have now completed the entire cycle. Actually, we completed it. Once this happened, but now we're back in, and now we've opened up a completely new ocean, and this is where we are right here. Well, we're not here yet. We're somewhere after that in between. Jurassic period landscape. Now we're getting some very big dinosaurs. The plant eaters have a lot of food. They have essentially outrun the growth evolution when compared to the predators. So the predators have to catch up. This might be an Allosaurus. It's kind of got the horns right here. Not so much horns as ridges, but the sauropods traveling in herds to protect the young. Meat eaters out here. You've got a somewhat lush landscape again. It's pretty warm during this period of time, and the dinosaurs are absolutely flourishing. And you can see that over time they've even, this design is just perfect for a large lumbering beast with plenty of food around. And the size alone is going to keep this from being a problem. Now, there's a bunch of these, it can be a problem, but even then, it's going to take a while for these to catch up. And over time, these actually begin to, I think only a few species make it into the Cretaceous, and by that point, they've evolved and they've shrunken considerably. Yet these guys have grown. So they developed something new in the form of armor and horns and clubs. All right, the Cretaceous period. The world is starting to look normal. Well, not normal. It's looking like something that we'd recognize. We have a huge interior seaway right here. We have the opening of the North Atlantic Ocean at 94 million years. The South Atlantic has also opened. The Tethys Ocean is getting subducted. India has ripped it off of Africa and Antarctica and parts of Australia. It is being dragged at an alarmingly fast rate across the Tethys Ocean. Lots of continental flooding in here. And again, this is why the dinosaurs are doing so well. They've got a flooded interior. They've got a shallow, warm sea with lots of food, and they are just loving it right now. I mean, this is like the best time you could ever be. Really, a dinosaur is probably in the Jurassic, later Jurassic into the early Cretaceous. It was the dinosaur heyday. And the world, this just shows it right here. And this is why Tyrannosaurs, Allosaurs, Triceratops, all found right in here. Right in here, they migrated, they were connected. You find a lot of dinosaurs here. Here, yes, you do in places. They're just harder to find because this is a tough area to get to. Not to mention some areas are wet, some are dry. The Alps have been created. The Himalayas have ruined a lot of stuff. So your dinosaur fields are really over here for the Cretaceous, the Jurassic and Cretaceous. And it makes sense. It's a nice warm seaway right here. And so the absolute right. Now, the reason I mention all this is because, well, what does it have to do with Maine? Well, what it has to do with Maine is that as you can see here, we were far away from an interior sea. Um, we had an ocean off here, but the problem is that whatever mountains we've had here, or whatever surface of land, whatever piece of land was at the surface where things could walk on, is long gone. So that's why we don't find many fossils. However, when we find the actual sediments of a Mesozoic time period, i.e., in Connecticut, guess what? There's dinosaurs there because that was actually the surface in the Mesozoic when the oceans opened in the early Mesozoic and the Jurassic in that area. These flood basalts allowed creatures to, because the flood basalts in the Connecticut Rift Valley are literally they're much younger than uh, than the um, the rocks surrounding them. So everything around that area is like early Paleozoic when there weren't even any land animals at all. So you're not going to find anything in those. So like when you walk from, if you were to walk from one side of the Connecticut Rift Valley to the other, um, let's say Vernon to Avon, you would be standing on Vernon Rock going down 84, and you would be in the order of three to 400 million years old, just metamorphic, wrenched, twisted, everything. Then you go into the Connecticut, the Hartford Basin, or through Hartford, and you're walking on rocks that were deposited in the Jurassic period, the early Jurassic when dinosaurs were around. And then when you go up over the hill and back down, you come back into 3 or 400 million year old metamorphic rock that's all twisted and banged up. But that point being is that that surface in between there was laid down at a time when there's dinosaurs, and guess what? We find dinosaur tracks. So there was probably dinosaur tracks all over New England, but those sediments have been long lost, and they're out in the Gulf of Maine, at least in this area, and probably off the continental slope in the form of muds and silt. So that's why we don't find. Plus, you know, not only first we didn't the rocks of the age around New England and Maine are mostly too old, so you're not going to find them. There weren't even really anything living on the land at the time anyway. But then you have to imagine that what we see above that of the younger rocks have all been scraped away. So the chances of finding fossils are very. Now you can find some, but it's pretty hard. There's some in Qatar. There's a few places you can find them, but it's because they were saved from being absolutely bent or metamorphosed or anything like that. So it's the rarity more so than the common. Cretaceous, 130 million years ago. This is starting to look like the North America that we all know and love. We got the Gulf of Mexico, Yucatan. I don't know. I guess Cuba might will come off here somewhere. The South Atlantic is beginning to open. This is probably going to be, well, if that's Newfoundland, then that's going to probably be Spain, Portugal. Sometimes, it's hard to tell. Blakey does such a good job with these maps. I mean, I don't know how he justifies everything, but I mean, looks good to me. The North Atlantic is continuing its opening right here, Greenland here, Norway here. 110 million years ago, everything's getting wider. North Atlantic is further extending. You have an interior seaway thriving with dinosaurs. You have the Gulf of Mexico. You have the Florida Peninsula here. The North Atlantic is starting to separate and become an ocean basin as well. You have the Laramide, or I believe it's Laramide. We'll just say the ancestral Rocky Mountain orogeny, and it is actually you still have a nice seaway right here, so the things are still doing well here, but it's not connected all the way through. Now it's all connected all the way through. This is sort of a high point of sea level in the Cretaceous. Well, actually, it was more in the Jurassic and early Cretaceous, but yeah, you have a really beautiful seaway right here. This is, like I said, you would have tons and tons of fossils, perfect for fossilization. That's why you find so many. The Arctic Ocean here, these accreted terrains are going to become, these are all accreted terrains, by the way. In other words, the boundary of Laurentia, North America, we call it now, would be here. These are all accreted. This is Alaska up here. North Atlantic is continuing its opening. We have, interestingly, another rift opening right here in the form of Greenland. Greenland could have gone this way as well. However, what we notice is that this for one reason or another stopped, and it probably had more to do. It just hit me. There is a huge hot spot that starts here, and it separates. I believe it assists in separating this, and it's the Iceland hotspot. And then it goes under Greenland, where it kind of gets capped and then just goes furious after that. And Iceland's kind of been there ever since. Oh, this is probably Cuba. I wonder how you done here. What the? All right, well, I'm going to find out what's up here. Well, I don't know where I left off, so I'm going to just assume that I finished the slide, and oh yeah, I did. Cuba was down there. Okay, so we know what's going on with this. The KT boundary, 65 million years ago. All of us know what this means. We know what's coming up. We know that it's the common theme of the asteroid hitting in the Yucatan Peninsula and causing absolute mayhem, which it did. But again, extinction events are never that clear and that crystal, and there's more to the story than that. And I do a 3-part series on that, which I'm going to have to redo because that was probably my first series I did. And if you think they're amateur now, you should see those. But there's a lot of good information in them, and here's a couple clues. One is, if you notice, you got this huge interior sea right here. Okay, this is wonderful. Animals love this. Anytime you have a nice swampy, warm, juicy area like this, animals thrive. Well, let's go to the extinction event at the end of the Cretaceous. It's gone. And if you live in that area when the ocean decides it wants to depart because sea levels are dropping, and sea levels drop for a couple of reasons. One is that the mid-ocean ridges began to slow down production. And that happened a little bit early. It happened, earlier on in the Cretaceous, but it's enough to initiate the draining of these seaways. And when these seaways drain, it's a real problem, because if you don't have your seaway there and you live in the ocean, you either evolve or die. And believe it or not, one of the hardest hit families in the KT extinction event is the mollusks. And it makes sense. Look what they had. They had all this area to thrive, and boom, they just got whacked because this dried up. Drying up alone is, and we see the progression of mollusks thinning out as you come up to the event. And guess what? Mollusks were probably a food source for quite a few things. So, you're starting to, you take one piece out of the system, and unfortunately, it affects every other piece when it comes to the food chain. So, yeah. Things are not doing very well, and this is your first clue. Almost every time there's a mass extinction, there is a drop in sea level, and over a short period of time. It's like clockwork. You drop the sea levels, stuff dies. That simple. Sea level encroaches continents. You tend to have diversification because you have more living places to live in, what have you. So anyway, 65 million years ago, Cretaceous. The paleogeography, about 100 million years ago, you still got your eroding Appalachian Mountains. Now you have a whole new mountain range with volcanoes out here. What on earth could that be? A volcano out here? Oh, New England hotspot. Yeah, that's a fun. I never caught that before. In any case, you've got the newly formed Rocky Mountains here. Again, I'm just hoping I get this right, so I have to go in and edit it, but I believe it's the Laramide orogeny. It might not be that. Anyway, one of the earlier Rocky Mountain, the ancestral Rocky Mountain orogeny, we know it's that. You got your volcanoes. You've got some subduction going over here, a nice trench. Um, you have the interior seaway right here, and you have what's left. These are probably more highlands now. They're not really mountains. They're probably highlands. And this right here, I believe, is representing the New England hotspot. The New England hotspot, over time, as the continent moves this way, travels through New England. No surprise there. Goes through, um, and then comes out, and there's all sorts of eruptions through here. Comes out, and then you can see the line of volcanoes going out to the mid-ocean ridge and beyond. So it's an interesting hotspot, and it's what Okay, it looks like I got it right. It was the Laramide orogeny. So thank God. I know my East Coast ones by the like the back of my hand, and I know most of the orogenies of the West Coast. I just mix up the timings of them. I mean, there's again, like the East Coast, there's a bunch of them. The Seaver, and it goes on and on. But I'm not doing a talk on the Rocky Mountains right now, so I can get away with it. But something I should probably brush up on. Cretaceous period landscape. We all know what this is. The king of beasts, the Tyrannosaur, in all its glory. And when I look at this, I just see I mean, what a masterpiece of evolution. We were brought to the brink, and then the reptiles over time just created this absolute perfect, just perfect carnivore. It's got a mouth, and I mean, what is this? What is this animal really? It's legs, giant claws for feet, and a mouth, and a body to consume whatever it eats, and one of the largest skulls of any known mammal. I mean, animal. Certainly some of the largest teeth of any known animal. A bite, a bite that has is probably one of the most powerful bites known in the animal kingdom. There are a few that can exceed it. It has now, binocular vision, so it sees straight, and it has just a massive amount of muscles around this jaw. And look at this neck. That's a Mike Tyson neck, man. I mean, that guy's got the biggest neck in the world. He's so strong, and it's like it's a back and then a skull. This guy is just built to kill. That's what he does. So you got your duckbills over here. This would be the preferred prey of these. Being that it can catch it. But there's always been debate whether or not he's a scavenger or a carnivore. Probably both. They say that if he actually tried to really run, he might actually shatter his femur. So I don't know. I find it hard to believe that something that is this designed this well could just be that slow. But maybe it was younger when it did it, and then as it got older, it was just sheer intimidation that would allow it to approach anything that was killed and eat it, because nothing's going to fight it off. So it probably evolved into a different type of eating when it was older. We know they grew quickly. I think that's the word, is that they grew very quickly through their adolescence. So, and that was important. If you're a dinosaur, it's probably a pretty brutal world out there, so you're going to want to get big quick. And then, of course, this. You don't really think about what it would have been like. I mean, I'm sure you think about what it would be like to be there, but to have something like that happen, even though you're not entirely aware, I mean, there's just no doubt in my mind, a creature of this size that has evolved for so many millions of years has enough sense to know that something seriously terrible is about to happen. And I just can't fathom what it would have been like. In my talk, I talk about how it likely produced a 11.0 earthquake, within a few thousand miles of it, and most likely a 9.0 worldwide. That's jarring enough to move, maybe a foot or more in less than a second. you know, that alone could kill you. Not to mention the rock falls, the avalanches, the tsunami, the air, the burning, the lahars. Well, it's not lahars; it's not volcanic, but the cloud, the pyroclastic flow that's going to come out of this. You know, it's just mind-boggling what could have happened, and to just wipe out creatures that evolved from one of from the worst extinction that ever happened to getting, they lasted almost 200 million years. I think 180 it was, to just get axed like that. And again, didn't just happen. The world was in rough shape already, but the ending was swift and severe, and without prejudice. It was just absolutely annihilation. So anyway, as I always end this, no explanation needed. And if it wasn't for this event, if these guys didn't get whacked, they survived as birds, and they're smart. If they were bigger, they'd be a problem. You really couldn't fight off a truly. If a bald eagle wanted to come down and get you, you'd have a hard time. It could kill you. It would not be hard. The talons are gigantic. So one can only imagine if these did not, what they would have evolved into, because it was the decimation of these and the cold that followed that allowed us, the mammals, to the second evolution of a reptile to take the earth. So anyway, there's Bella, and I just want to say Merry Christmas to everybody, and thanks for watching, and be safe. Aloha.